All right. Good morning, everyone, especially to Ayesa, Michael, Prince, John Christian, and Trisha. So welcome to Unit 5, last unit na ng course. Yay, matatapos na. Pero dahil patapos na ang course, so we still have how many? I think we'll still have a couple of homeworks, one or two more homeworks. And then we'll have the third problem set, which I'll give probably when we are three quarters down with the current module para naman mapaaga tayo ng kaunti. Siguro 3 or 4 days earlier than other ACADS or than your other problem sets o mga major ACADS requirement towards the ends of the SEM para masimulan nyo na siya paunti-unti. So because my target there is end of classes, sana yun yung deadline natin for actually 155, no? Pwede palang gawin natin siguro hanggang first week ng finals yung ang dami niya pala, no? Ang gulo ko. So I'm thinking, sige, last day of classes sana yung magiging deadline natin ng problem set number 3. Tapos para makapag-focus sa kayo sa iba yung ACADS during the finals week. And as I've mentioned, our final exam is quite easy. You'll just need a couple of hours to finish it. It's going to be just a reflection paper dun sa experience niya about Math 155. So, but please be truthful and medyo detalyado dun sa pagsusulat because I really grade the content. Binabasa ko yun line per line. So, para makita ko ano yung natutunan nyo kung meron man dito sa kursong ito. Ano? And then I'll also release a survey or an evaluation form on how you think this course was handled para sa personal growth at saka saka sa improvement for this course if and when I will handle it again next year. All right. So those are the plans for the next 3 weeks or so, or next month of the semester, the final hurrah for the second semester of this academic year. Pero sige, back to the present tayo. We will start now module number 5, the last unit in the course, and this will be about integration, right? So dito, titingnan natin yung isang alternative development ng integration on a theory of integration. Of course, you have seen the same processes nung nag-math 30 series na kayo, but I think there you defined the integral as the limit of the Riemann sum, which is basically equivalent talaga dun sa gagawin natin. Pero ibang flavor yung gagawin natin, i-develop natin siya independent of the limiting procedure, okay? So, though kaya siyang i-rephrase using limit definition, pero medyo kasi pagka nagsabi tayo ng limit or hindi, ang problema pala kasi talaga, hindi tayo nag-focus masyado dun sa limits at infinity. So kasi sa Riemann sum, dun sa definition nyo ng Math 36, kinukuha nyo yung limit ng Riemann sum as the number of subintervals n approaches infinity. But we didn't focus on that. So I ought to give you an alternative development of the theory of integration that will fit dun sa natutunan natin from chapters 1 to 3. So basically, we'll be going through sequences or some properties of real numbers, infimum, supremum, etc. So yun yung promise sa unit na to. Another particular thing is that we'll try to make it more general than our Math 36 definition. Tama ba ang pagkakalala ko? Sa Math 36, parang ang tinignan lang natin ay integrability ng mga continuous functions. Tapos special cases lamang yung mga functions na discontinuous and yet kaya natin silang kunan ng integral. So parang naging special case na lang siya. But here, we'll build the definition of the integral from a more generic point of view, right? So we will not require continuity for integration. Actually, the promise is titingnan natin gaano siya ka-discontinuous and yet magkakaroon pa rin siya ng integral. Because we will prove that any continuous function is integrable or mag-exist ang kanyang integral. But continuity is not necessary. Okay? Kung differentiable kung integrable ka, hindi ibig sabihin na ikaw ay continuous na because there are discontinuous functions that are integrable. So titingnan natin yon. Tapos magbibigay tayo ng criteria or criterion. Ano yung pwedeng mangyari or ano yung i-allow natin na level of discontinuity para siya ay maging integrable pa rin. So that's basically what this unit will focus on. And this will have 4 chapters. So first, we'll define, hopefully today, the concept of the Riemann integral through upper and lower Riemann sums. And then we'll go over and look at some integrability criterion because employing the definition is quite hard. Kasi kailangan nating tingnan yung lower Riemann sum, upper Riemann sum, titingnan natin yung infimum at saka supremum nila, kung mag-equal yung dalawa saka siya integrable. That is a very tedious and daunting task. So sa section 2, titingin tayo ano kaya yung mga sufficient conditions para masabi natin na integrable ang isang function. And then we'll move forward to section 3, which will give us the basic properties of the Riemann integral. Some of them nakilala nyo na from Math30 series, probably without proof, but here we will just substantiate those results. And then lastly, we'll cap the course off with the nice statement of the fundamental theorem of calculus, because the course will not be complete if we will not be mentioning at least yung pinaka-fundamental na result mula sa calculus. After all, this is a calculus or this is an advanced calculus class. Kaya marapat lamang natapusin yung kurso sa fundamental theorem ng calculus. Okay, so that's the program, that's the agenda for the unit. And probably once we hit off section 3, I can give you problem set number 3. Ibibigay ko na yung buong problem set 3 para masimulan nyo na siya. Okay? So kahit nag-discuss pa tayo ng unit 5, pwede nyo simulan yung nandun sa unit 4 at saka unit 5. Actually, probably I can give it next week na. So just give me a couple of days to think about the questions that I'll put there. Tapos bibigay ko na sa inyo para pwede kayong mag-work on that until June 9. Okay ba yun? O gusto nyo kung kailan na lang siya due or 1 week before it is due saka ko siya ibibigay? Pero anyway, mas okay kaya na i-release ko na siya ng maaga, and it's up to you if you want to start early or not, right? Basta ang usapan natin, ang target deadline natin hopefully ay by June 9th, all right? Which is the last day of classes. Okay, so let's start. So, bubuuin natin ngayon yung konsepto ng Riemann integral. Tingnan ko lang ano yung introduction. Okay, yeah. So, pero medyo limitado tayo rito kasi titingnan lang natin dito ang definition ng Riemann integral ay para sa mga bounded functions. Alright? So, if you want to talk more about the case of unbounded functions, probably you'll need to take Math 156. Kung di siya covered sa 156, probably in some other elective courses, right? But yeah, we'll focus more on the bounded functions kasi kailangan natin yung konsepto ng maximum o minimum o kaya supremum at infimum ng mga functions para ma-define yung Riemann integral, right? And to do that, because we are starting from scratch, we are rebuilding everything from the ground up. So simulan natin dun sa mga necessary definitions bago tayo makarating sa Riemann integral. So una, definition 5.1, we'll be talking about a partition inducer. Okay. So we say that a finite ordered set x sub 0 until xn is a partition inducer of the closed interval AB if P consists of points in increasing order starting from A to B that are inside the closed interval AB. So magiging partition inducer siya kapag ka meron kang yung set x0, x1, x2 hanggang kay xn ay magiging isang partition inducer kapag ka si A magiging partition inducer siya ni closed interval AB if A is equal to x sub 0 and B is equal to xn, and the smaller the subscript, the smaller the number is. So dapat talaga naka-order sila pag ganun. Tinawag ko siyang partition inducer kasi itong mga finite points na ito, nakakapag-generate sila ng partition ng closed interval AB. So tandaan nyo ba yung ibig sabihin ng partition? Pa-reciting ko kaya si Prince saka si Trisha kasi students ko sila ng 101 last semester, so dapat alam nila kung ano yung partition. We say ang isang collection of sets is a partition of a bigger set if disjoint yung mga sets na yon na nasa family. Tapos ang union nila ay yung buong yung buong set mismo. At saka ang bawat isang element ng bigger set ay nasa isang element lang ng partition. So in this particular case, we say that the closed interval x0 to x1, the closed interval x1 to x2, the closed interval x2 to x3, and so on until the closed interval x sub n minus 1 to x sub n induces sort of a partition. Basta wag mong halimbawa, wag mo lang pagsasamahin yung wag mo lang isasama halimbawa si x2 dun sa dalawang intervals na magkasunod. Pero anyway, tapos ang union ng mga intervals na yon ay equal sa interval AB. So parang etong elements ng partition inducer, ito yung nagsasabi sa atin kung paano natin hati-hatiin yung closed interval AB into smaller closed intervals. So yun lang yung ibig sabihin ng partition inducer. Okay? So it is a partition, the partition inducer, as I've mentioned, is a finite ordered set. So crucial dapat na nasa-satisfy itong inequality na to. Alright? Para lang magkaroon lang ng sense yung mga intervals na ipapakita ko sa inyo later. Okay? And then we will also denote, or we will also let delta of x sub I, or the change in x sub I, to be x sub I minus x sub I minus 1, or that's going to be the absolute value of I sub I. Yung I sub I, siya yung closed interval, starting from x sub I minus 1 hanggang sa x sub I. Tapos usual notation nito, pag nilagyan mo ng absolute value ang isang interval, ibig sabihin yun yung haba nung interval na yon. So basically, the length of the ith subinterval or the ith partition induced by the partition inducer P is equal to the right endpoint minus left endpoint. So yun yung haba. And we will denote that length by delta xi, or the change in the x sub i's. All right? Now, as an example, say our interval of interest is the closed interval 0, 2, then the set P1 consisting of 0, 1, 2 is a partition inducer because yung unang element niya at yung huling element niya corresponds to the first and last elements of the closed interval respectively. And then everything in the middle is arranged in increasing order. So it's a partition. Ganun din yung nangyari kay P2. Okay? So dalawang magkaibang partition inducer, pero tingnan nyo itong left endpoint, right endpoint, and then the intermediate points are in increasing order. So P1 and P2 are both partition inducers of the closed interval AB 0, 2, even though they do have different number of elements. Okay. Meanwhile, P3 and P4 are not partition inducers. Can somebody tell me why P3 is not a partition inducer? Tapos P4 din. Sige, volunteers? Para may time ako mag-sip ng coffee. Bakit yung P3 or yung P4, pick your poison, kung sino yung gusto nyo sagutin, bakit sila hindi partition inducer? John Christian, nakita ko, tinaas mo kamay mo. So you wanna recite? Okay, yes, Ayesa. Sinagot na ni John Christian yung P3, so Ayesa, P4. Sa type ka rin ba, Ayesa? Mga shy type kayo, no? Ayaw nyo mag-open ng mic. Okay, tingnan natin. Si John Christian, ang sabi niya ay ang x3 ay mas malaki kesa kay x2. Si x3 mas malaki kay x2, kay P3. Ito ang x3 mas malaki. Oh, yung baliktad. All right. Thank you, John Christian. Yeah, John Christian is right. Because here, hindi naka-increasing order yung mga elements ni P3, right? It could have been a partition inducer kung nabaligtad lamang yung order ng second and third elements ni P3, right? Actually, magko-coincide na siya by P2. Actually, ang dahilan lang kung bakit gusto ko sila ay in increasing order para mag-make sense yung definition ng length ng interval. Because if I will use this notation, interval 1, interval 2. Yung length ng I2 magiging 1/2 minus 1 ay negative 1/2. So I don't want to do for that to happen. So kaya nire-require natin na increasing order. But other than that, pwedeng matweak yung definition pero para lang organized yung pagkaka-define natin. Gusto natin increasing order yung mga elements ng partition inducer. And then, thank you, John Christian. And then Ayesa is right. Kasi kasi si x sub 0 kay P4 ay hindi equal kay A. That's correct. Because the interval of our interest is the closed interval 0 to 2, but the partition inducer started at 1. So P4 is not the partition inducer of 0, 2 because the closed intervals that P4 induces will not cover the entire interval 0 to 2. Ang usapan, dapat hatiin natin yung 0 to 2 into a partition. Pero pag ito yung ginamit nating markers dun sa partition, hindi makakasama yung mga numbers na nandun sa closed interval 0 to 1. But you can say that P4 is a partition inducer for the closed interval 1, 2, but for the closed interval 0, 2, it isn't. All right? So that's perfect. Thank you, Ayesa. So yun lang yung kailangan ko, konsepto ng partition inducer, and then we can proceed into defining the lower and the upper sum. Sometimes we call it the upper and the lower Riemann sum. Okay, so ano yung sasabihin niya? The upper sum of f with respect to, so actually ginagamit na natin dati yung WRT pa, no, na with respect to. So the upper sum of f with respect to the partition inducer P is given by this formula. So essentially, ang sinasabi niya, kung meron ka ng partition inducer, tapos meron ka halimbawa bounded function dyan, okay? So dun sa bawat isang interval, so halimbawa, first interval tayo, kukunin natin yung supremum. Let me just double check that. Yeah. Kukunin natin yung supremum nung mga function values sa lahat ng x sa bawat sub-interval ni AB. Okay? So halimbawa, ito yung I1 natin, yun yung kauna-unahang interval. We will look at what is the supremum of the function over the closed interval x0 to x1. And we will assign that to be the function value. Halimbawa, nasan ba yung maximum? Pangit kasi pangit yung napili kong dinrawing kong curve. So hindi obvious yung maximum. Yan, para medyo obvious yung maximum. Nandun tayo sa closed interval AB, ito yung maximum niya. So, ibig sabihin, yan yung i-consider ko. Ito yung capital M sub I. Ito ay equal sa, okay, good. Supremum ng mga f of x's, where x's belong to I1. Alright? So, siya yung equal dyan. Tapos, i-assign ko sa I1 yung number, which is basically the area of the square whose height is the highest function value and the width is the length of the ith interval. So, ibig sabihin, the drawing ko to, yung rectangle na to, yung area ng rectangle na yan would be the supremum function value, which is m sub 1, nating m sub 1, times the length of the ith interval, which we said tatawagin natin yung x sub 1. So, yun yung weight na, yun yung value na i-assign natin sa first interval. And then we will do it for all the other subintervals, okay? Now, if our function f is assumed to be bounded as promised earlier, then the supremum will exist. All right? Pero kung hindi bounded si f, magiging infinite na kagad yung etong sum na etong value na to. So hindi na magiging real number yung upper Riemann sum. Okay? Because the upper Riemann sum is the summation ng lahat ng mga areas ng mga rectangles. And you will see that this is very similar to how you develop the Riemann integral in Math 36 na yun nga lang ang usual choice natin ay yung left endpoint o kaya yung right endpoint o kaya yung midpoint, no? Pero another way of doing it is choosing the supremum or the maximum function value on the ith interval tapos yun yung gagawin yung Riemann sum. For our case, ang upper Riemann sum, ang pinili natin na height ng rectangle ay yung supremum ng mga function values, yung pinakamataas na point doon sa closed interval x sub 0 to x1. All right? And then we take the summation of all the areas of the rectangles induced by the partition inducer, and what we'll get is the upper Riemann sum we denote by this. Now, we always include these arguments because the upper Riemann sum depends, of course, on the function f. Kasi yung function value na gagamitin nating height nakadepende kung ano si function f. And it is also dependent on the partition inducer. So if you have the same function f, the same closed interval AB, but two different partition inducers, then you might have two different upper Riemann sums for that particular function, because the upper Riemann sum depends on the partition inducer that you chose. Okay, so meaning if you go back to our example, if you have, say, a function, say x squared, defined on the closed interval 0 to 2, then you calculate the upper Riemann sum corresponding to P1 and compare it to the upper Riemann sum induced by P2, then you might get two different results. Okay, kasi nga iba-iba to kasi si U nakadepende sa function at saka sa partition inducer na pinili natin. All right? And analogously, we define the lower Riemann sum of f with respect to the partition inducer P. Now, we still are looking for the areas of rectangles, summing them up over the possible rectangles drawn using our partition inducer, but this time the height of each of the rectangles will be the infimum of the function value. So you'll be looking at the smallest, or anong antonym ng tallest? Shortest. You'll be looking at the shortest, or the areas of the shortest rectangles possible on each of the subintervals. And that's what we will call the lower Riemann sum. Okay? So is everything clear so far? Upper Riemann sum, lower Riemann sum, partition inducer. Okay, I hope it is. Now, one quick property that we can deduce ay laging mas malaki pag fixed si function f at saka fixed din yung partition inducer, then we can say that the lower Riemann sum is always less than or equal to the upper Riemann sum. Kung parehas nga lang sila ng partition, edi ibig sabihin pare-parehas yung subintervals na pinipili natin. Yung upper Riemann sum madaya kasi ang pinipili niya yung mga pinakamatangkad na triangle, na rectangle, yung pinakamatangkad na rectangle dun sa bawat subinterval. Yung lower Riemann sum, ang pinipili niya naman na value para dun sa ith subinterval ay yung pinaka-short na rectangle. So definitely, by definition, the lower Riemann sum of f with respect to the partition P is always less than or equal to the upper Riemann sum of f with respect to the same partition P. Moreover, if f is continuous on the ith subinterval, which is a closed interval and therefore is compact, then it will attain the supremum, it will attain a maximum and a minimum on the ith subinterval, and that maximum and minimum will automatically be the supremum and the infimum on that interval. Medyo generic kasi yung pagkaka-define, supremum, infimum. Pero kung si f ay continuous, ibig sabihin si m sabay, hindi lamang siya yung supremum, siya na rin yung maximum. And then yung little m sub I, siya na yung minimum, hindi lamang siya infimum. Because I hope by now it is clear what's the difference between the maximum and the infimum. Yung maximum, siya lang yung pinakamalaking function value. Yung supremum, siya yung least upper bound ng mga function values. So the supremum need not be a function value itself. All right? Pero kapag continuous yung isang function sa isang closed interval, which is compact, yung maximum siya na rin yung supremum. All right? So yun yung kanilang yun yung kanilang relationship with each other. And then I forgot yung kunento ko pala na example kanina. Gagawin pala sa example 5.2. So here we consider, actually isa lang pala to. So okay lang pala na spoil ko kanina. So we consider the quadratic function x squared on the closed interval 0, 2. And we consider one partition inducer, yung partition inducer 0, 1 half, 1, and 2. Tapos titingnan natin ano yung lower at yung upper Riemann sum para sa function f relative to or with respect to the partition P. Okay? Now, dahil ito yung partition P natin, or yung partition inducer P natin, magkakaroon tayo ng tatlong subintervals. The subinterval 0 to 1 half, 1 half to 1, and the interval 1 to 2. I1 has length 1 half, I2 has length 1/2, and I3 has length 1. Tapos para mabuo sa yung lower Riemann sum, titingnan natin ano yung pinakamaliit na function value ni x squared all throughout those three subintervals. Now, what do we know about x squared? X squared is an increasing function from 0 to positive infinity, so the minimum will occur at the left endpoint. So that's why here on I1, the smallest value of x squared, which will turn out to be its infimum as well, is 0 squared. So you got 0 here, and then the length of the interval. Lowest function value on I1 would be given at x equals 1/2. So that's going to be 1/4, yung function value. The length is 1/2. And then for I3, the smallest function value is 1, and the length of the interval is 1. So we'll have 1 times 1 in the third term. You take the sum, we'll get 9/8. And that's the lower Riemann sum of f relative to the given partition inducer P. On the other hand, if we want to compute the upper Riemann sum, titingnan naman natin yung highest possible value sa bawat subinterval. Our I1 is 0 to 1/2. Length is 1/2. Highest function value here will be given by the right endpoint. So 1/2 squared will get 1/4. Second subinterval is 1/2 to 1. Its length is 1/2. Highest function value is 1 squared, which is 1. And lastly, we'll have 1 to 2. The length is 1. Highest function value would be at the right endpoint, so that's going to be 2 squared. So we got the upper Riemann sum is 37/8. And clearly, 37/8 is larger than 9/8 as promised. Okay? So this is nothing new. I guess you already did something like this in Math 36. Yun nga lang baka left, right, saka midpoint yung ginamit nyo. Dito, kukunin natin yung maximum at saka minimum. Okay? All right, now we're ready for defining the upper and lower integral. So itong dalawa ay upper at saka lower sums pa lang or Riemann sums. Ngayon, paano natin siya i-convert into integrals? And that's in definition 5.3. So dito, i-assume natin si f ay bounded. The reason again why I'm assuming f is bounded ay para alam ko na mag-exist yung infimum at supremum. So bawat term dun sa upper at saka sa lower Riemann sum ay well-defined. Okay? Sila ay mga real numbers. Nag-exist silang lahat as real numbers. So kaya kailangan ko na bounded yung isang function. And then we define the upper integral of the function f on AB to be the infimum of all the upper Riemann sums relative to any partition inducer of the closed interval AB. Tapos ang notation natin sa upper integral ay this guy. All right? So it's your usual integral, definite integral, may function f. Dahil wala naman ditong problema about what the variable of integration is, hindi na natin sinasama yung dx sa Math 36, sa Math 155. Actually, sa higher analysis, hindi na nga sinasama yung dx o d sigma pagka clear naman sa context kung with respect to saan ka nag-i-integrate. Tapos maalala niyo yung teacher niyo ng Math 36, siguro galit na kapag wala yung dx dun sa integral. Ano? Pero ngayon sa Math 155, ito yung high-tech nating notation. So it's the integral from a to b of f with an upper bar. That means it's the upper integral. How do we compute the upper integral? It's the infimum ng lahat ng posibleng upper Riemann sum. Kasi sabi natin yung upper Riemann sum magbabago yan kapag kahit si f ay constant or hindi nagbabago or fixed, pero yung depende na yun sa partition inducer na pinipili mo. Typo here, this should not be a curly p. It should be a straightforward p. Ano? Kasi kukunin mo lahat ng posibleng upper Riemann sum, tapos kukunin mo yung greatest lower bound ng mga upper Riemann sums. Alright? So yun yung pagko-compute ng upper integral. Then the lower integral with the following notation is similarly defined, but this time it is the supremum among the lower Riemann sums. So for all possible partitions, so P ito, sa lahat ng posibleng partition inducers ng closed interval AB, computein mo yung lower sums. Tapos pag na-compute mo na lahat ng lower Riemann sums, kunin mo yung least upper bound ng mga lower sums na yon, makukuha mo yung lower integral. Okay? And then a function becomes Riemann integrable or simply integrable for now, yun ang tawag natin, integrable, sa closed interval AB kapag ka nag-coincide yung upper at saka yung lower Riemann integral. Okay? And moreover, we say that the value of the integral or the Riemann integral of f on the closed interval AB is equal to the common value of the lower and the upper Riemann sums. Okay? Medyo nag-criss-cross yung pagma-maximize, pagma-minimize, right? Kasi yung upper Riemann sum, kukunin natin yung summation ng mga areas ng rectangles where the heights are the supremum or the suprema of the function values all throughout the subintervals. Tapos pag nakuha mo na after taking suprema, kukunin mo yung infimum. Dito baliktad naman. Para ma-compute yung lower Riemann sum, kailangan mong kunin yung infima ng function values sa bawat sa mga subintervals. Tapos pag nakuha mo na yung mga infima o yung mga rectangles base sa mga infima, kukunin mo yung supremum. Alright, so crisscrossing ito. Pero ang idea kasi, yun yung tanging paraan para mapagtagpo natin yung lower at saka Riemann sum. Because if you will plot yung mga lower at saka mga upper Riemann sums, yung mga upper Riemann sums, nandito sila. Upper Riemann sum, so F, say P1, posibleng nandito yung upper Riemann sum F with respect to P2, tapos nandito lagi yung mga lower Riemann sum. Okay? Kasi di ba laging mas maliit yung mga lower Riemann sum kaysa sa mga upper Riemann sum. Tapos ang idea natin sa integrability ay dapat mag-equal yung lower at saka upper integral. Alright? So kaya ang ginagawa natin, dinefine natin yung upper integral to be the infimum. Siya dapat yung greatest lower bound ng mga upper sums. Kasi nga yung mga upper sums, lagi silang mas malaki sa mga lower sums. So ibig sabihin, para mapagtagpo natin yung mga lower sums at saka mga upper sums into one common value, we want to drive the upper sums down, pababain yung value nila, kaya kinukuha natin yung greatest lower bound. Kinukuha natin yung infimum ng mga upper sums para mapababa natin siya ng konti. Hindi masyadong mababa kasi gusto natin yung greatest lower bound. So bababa ng konti yung value nila, tapos hopefully ma-meet siya halfway nung supremum o nung least upper bound ng mga lower Riemann sums. Kasi mas mababa yung value ng mga lower sums, right? So kung kukunin ko yung supremum ng mga lower sums, medyo makakakuha ko ng mas malaking value. And we're keeping our fingers crossed na sana yung LUB ng mga lower sums at yung GLB ng mga upper sums ay mag-meet sa isang common value. And this common value is what we will call the Riemann integral of f over the interval AB. So ganun yung mangyayari. Check natin yung supremum, infimum para malaman kung siya ay integrable o hindi. Okay? Does that process make sense? Mahalaga to kasi all throughout the unit, ito yung pagbabasihan natin. Or nakadepende yung mga proofs o yung mga results from this idea of the upper and the lower Riemann integral. Everything is good pa? Or super basic pa naman niya? Kaya okay lang. Oh guys, ba't di kayo nagre-react? Hindi pa rin kayo nakaka-move on sa anxiety or pagiging disheartened nyo last week. I know it's hard. Medyo may episodes pa rin ako, pero trying to move forward. Kasi wala naman tayong choice, ano? So I hope everything is okay pa. Okay, so siguro let's reinforce that definition by some illustrations. So tingnan natin yung illustration 3. So illustration 3, papakita natin na integrable ang constant function f of x, say a constant c, sa kahit anong closed interval AB. Alright? So medyo madaya nga lang itong example. Napakasimple niya. Kasi sa totoo lang, ang hirap i-implement ang definition 5.3. Kasi nga, kukomputin mo lahat ng mga posibleng upper Riemann sums. Essentially, you're getting a formula for the upper Riemann sums. Pero ang siste rito, kailangang i-take natin lahat ng posibleng partition inducers. Kasi sa partition inducers, ang daming posibilidad. Ano? So, basta na-satisfy yung definition 5.2, partition inducer siya. So, hindi fix yung number ng mga elements ng partition inducer, hindi rin fix yung elements nila, so posibleng maraming mga partition, hindi pala posible. Talagang infinitely many, uncountably many yung partition inducers. Tapos kukuha ka ng formula para sa upper Riemann sum para mas madali mo makita yung infimum. And that's very difficult. Ano? So kaya ang goal ng succeeding parts of this unit ay bigyan tayo ng mga sufficient conditions para sa Riemann integrability by looking at the properties of the lower and the upper Riemann integrals or sums para hindi na tayo babalik dito sa definition over and over again. Pero just to give us a tangible idea about how this definition works, let's consider some elementary functions. Unahin nga natin yung constant function f of x equals c. Now, dahil constant lang naman yung closed interval a, b, okay, titingnan natin, madaling kunin yung formula para sa lower at saka sa upper Riemann sum. Kasi kahit paano natin hati-hatiin yung closed interval AB, all right? Sa kahit ilang partition, kahit anong partition inducers, kahit ilan yung element ng partition inducers, constant lang naman yung value nung function all throughout the interval. So the infimum and the supremum of the function values over any subinterval will just be equal to the common value c. All right? Ito ay equal lang kay c. Ito ay equal lang din kay c. Kahit mapaano pang partition inducer yon. Ang mahirap lang naman talaga dito ay yung paghahanap ng maximum at saka minimum o ng supremum at infimum. All right? So, but since the function is constant, then little m and capital M are both equal to c for any subinterval. Okay? Dahil equal na siya kay c, constant siya, independent of I. So, pwede siyang lumabas ng summation. So, we get these two guys over here. Tapos, summation ng delta x sub I. Ano nga ba yung delta x sub I? Ito lamang yung haba ng bawat interval. So, this summation is just asking us to compute the total length of the subintervals. But since we have a partition inducer, yung union ng lahat ng subintervals ay equal dun sa original interval given. All right? So the length of the sum of the lengths of the subintervals will be equal to the total length of the closed interval AB that was partitioned earlier, and that is equal to B minus A. So essentially, any lower Riemann sum will be equal to C times B minus A. And in the same token, any upper Riemann sum will be equal to C times B minus A. Tapos para makuha yung upper integral, all right? So yung upper integral ay infimum ng mga upper Riemann sums, the greatest lower bound among the upper sums. But all the upper sums are equal to C times B minus A, so the greatest lower bound for them is C times B minus A. So we can say that this guy is also our upper Riemann sum. Okay? And similarly, ganun din yung nangyari sa lower Riemann sum. Actually, C times B minus A is the lower Riemann sum of F. And since they do have the same value, then integrable yung constant function sa kahit ano pang closed interval with the value of the Riemann integral being equal to C times B minus A. Okay? Is that good? Siyempre, hindi na naman kayo mag-react. So, magpo-proceed na ako sa example 5.4. Unless may violent reaction o may magchat-chat na, sir, pakiulit nga po, I'll be happy to accommodate you. Ano? So, tingnan natin yung example 5.4. Ito yung isa sa mga function na hindi natin kayang bigyan ng integral sa Math 36. Okay? Or hindi natin ni-consider sa Math 36 kasi isa tong discontinuous function. Ito yung tinatawag natin na Dirichlet function. If I remember it right, we have encountered this before. Tama nga ba? Nung nag-usap-usap tayo about limits, this is one of my may examples before ng isang function na walang limit. So, tama ba? Walang limit? Or something like that. Alright? So, ito ay hindi natin nabigyan ng value ng integral sa Math36 definition. Pero napakasimple kasi ng function na parang imposible na hindi natin siya pag-usapan insofar as integration is concerned. Okay? Kasi dalawa lang yung posibleng value ni f. Ano nga ba yung dalawang, paano natin nako-compute yung value ng Dirichlet function? The value is equal to 1 if the input x is a rational number on the closed interval 0, 1. So, define siya sa 0, 1. Kapag ka si x ay rational, ang value niya ay 1. Kapag ka siya ay irrational, ang sagot ay 0. Okay? So, para tong characteristic function lang o check function kung ang isang element ni x ay member ng rationals on the closed interval 0, 1. Pag rational si x, 1 ang value niya. Kapag ka irrational si x, 0 yung value niya. Tapos tingnan natin, ano yung upper at saka Riemann integral? And do we have an integral for the function f? Now again, we go to the process of looking for the upper and the lower Riemann sum. Now, kailangan natin itong gawin in a generic fashion na dapat lahat ng posibleng partition inducer ay nako-consider. Okay? So meron tayong closed interval 0, 1. Tapos halimbawa, ito si x1. Okay? So, si Dirichlet function ay either 1 or 0. Nakadepende lang siya kung yung x ay nandun sa set of rationals or wala. Okay? Kaya lang, si 0 at saka si x1, pareha silang real numbers. Okay? Kahit ano pa si x1, basta nandun siya sa open interval 0, 1, pareha silang real numbers. And by the density property of Q on R, sa pagitan ng kahit anong dalawang real number, merong rational number. So, ibig sabihin, meron ditong isang rational number, so it will attain the function value 1 on at least one point between 0 and x1. Tapos yung 1 na yon, sure tayo, siya na yung maximum over the first subinterval. Okay? And this will happen all throughout all the other subintervals induced by the elements of P. So, ibig sabihin, laging supremum si 1. Kasi sa pagitan ng dalawang endpoints ng subintervals, laging may rational number. Kaya yung m sabay, laging equal kay 1. On the other hand, if we look at the lower Riemann sum, we need to look for the infima on these subintervals, right? Yun yung m sabay. Okay? Ano ba yung infima? Well, dahil bounded naman si Dirichlet function, yung infima, siya yung mga infima, sila ay equal sa mga minima, right? So tingnan natin yung minimum value ni f sa bawat subinterval. Well, 0 and x1 are both real numbers, so by the density property of Q complement on the set of real numbers, meaning between any two real numbers, there is always an irrational number. So we can always find an irrational number between 0 and x1. And that irrational number will give us the minimum value 0 on any of the subintervals. So lahat ng little m sabays ay equal kay 0. Okay? So kahit ano pa si partition inducer P, si upper Riemann sum ay laging equal kay 1 times the length of the interval. Kasi itong 1, lalabas siya, summation ng delta xi, alam na natin yan ay b minus a lamang. B minus a in our case is 1. So the upper Riemann sum is always equal to 1, and the lower Riemann sum is always equal to 0. Constant yung term. So constants yung upper at saka lower Riemann sum. So therefore, this is our upper integral. Kasi ito na rin yung infimum ng mga upper sums. Dahil constant yung lower sum, siya na rin yung supremum ng mga lower sums. So this is our upper integral. This is the lower integral. And since they are not equal to each other, we say that the Dirichlet function is not Riemann integrable. Okay? Everything's good? Sorry pa, ulit-ulit ko yung tatanungin kasi pagka ganon, pag nagtatanong ako at kunwari nag-aantay ako ng sagot sa inyo, kahit alam ko na naman na hindi kayo sasagot, nagsisip na lang ako ng coffee. So, yun na lang yung makukuha kong benefit from asking you. Okay? So, let's try to establish some properties. Hindi na gana yung reactions, Michael. Bakit kaya? Or isa pang posibleng dahilan ay mabagal yung internet ko kaya hindi ko nakikita yung reactions. Pero sa 175 nagre-react naman kayo. Bakit dito hindi? Bigla nagtampo no? So now, let's try to prove some properties for the upper and the Riemann sum para makapag-establish tayo ng integrability criteria. Okay? So, tingnan natin tong inequality na to. Bakit yan totoo? Actually, madali naman siya makita. So, sabi rito ay lahat ng lower sums ay less than or equal to sa lower Riemann integral. And that should be what you call this? That should be obvious, all right? Bakit siya dapat maging obvious? It should be obvious kasi nga ang lower Riemann sum, oops, eto na naman siya. Kahapon pa yun sa 175, hindi ako nagcha-charge ng pen. All right? So kasi ang lower Riemann sum, itong lower Riemann sum ay laging sa ano nga definition nito? Ito yung supremum ng mga L. So ibig sabihin, in the first place, the lower integral is an upper bound of the lower sums. Therefore, this inequality is obviously true. All right? Tapos, on the other hand, yung upper Riemann sum naman, siya naman yung infimum ng mga U. Right? So, ibig sabihin, in the first place, the upper Riemann sum is a lower bound of the upper sums. Sorry, ano sabi ko? Tama ba sinabi ko? The upper Riemann sum is always a lower bound of the upper sums. So therefore, this inequality must be true. Okay? So obvious na siya. So ang hindi na lang masyadong obvious ay etong inequality na to. So etong nasa gitna. Na mas malaki lagi yung upper Riemann sum kesa sa lower Riemann sum. Pero I hope this and this inequality are clearly true. Right? So for that, we'll prove the middle inequality in one of the following lemmas or lemmata. Okay? So tingnan lang natin yung mga results na dadaanan natin para makuha yung result na yan. So dadaan tayo sa lemma 5.1, which establishes this inequality for any partition inducer P. So kung fix si F, which is bounded with maximum M, with minimum little m, and maximum upper M all throughout the interval, then sabi niya itong inequality na to ay totoo. Okay? Now, little m here is the infimum and capital M is the supremum on the interval A, B. So, pwede ko palang binura na lang ito. Sinabi ko na lang dapat if F is bounded on AB. Sorry, real-time nag-edit. And P is a partition inducer of AB, then I think this makes sense now. Okay? So, dapat daw totoo itong inequality na to where little m is the infimum function value and big M is the supremum function value. Right? So, paano natin to maprove? Ang idea rito ay dapat sa kahit anong partition inducer. Okay? So now I cannot impose any specific partition inducer, so we'll work in a generic term. Pero sa bawat interval say I sub I of any partition induced by any partition inducer, totoo itong inequality na to. Okay? Why is it true? M is the infimum all throughout the interval AB. So ito yung sort of minimum sa buong interval AB. So yung minimum sa bawat interval ay dapat mas malaki dun sa minimum over the entire interval. Tapos yung maximum sa bawat interval, sa bawat sub-interval, ay mas maliit dapat dun sa maximum doon sa buong interval AB. Kasi parang ganito yung mangyayari. Oops. Ito yung function f natin on the interval say AB. Okay. So yung yung little m natin ay ito. Yung ating big M ay ito. Kasi si little m at saka si big M, sila yung infimum at supremum on the entire closed interval AB. So halimbawa, meron ng partition inducer dito. Halimbawa yan si X1. dun sa unang interval x0 to x1, ito yung ating infimum. Yan yung si little m sabay. Tapos, ito yung ating capital M sabay. Dahil kokonte yung options doon sa interval a to x sub 1, posibleng hindi mapasama yung pinakamaliit sa buong closed interval. So the minimum on this subinterval must be larger or equal to the minimum doon sa buong interval. So clearly, mas maliit pa rin tong mas maliit sa buong interval, right? Tapos dahil kakaunti rin yung option mo para sa maximum o para sa supremum, yung makukuha mong supremum dito, posibleng mas maliit kaysa dun sa supremum dun sa buong closed interval. Okay? So yun yung idea nitong inequality na ito. So any infimum or maximum on your subintervals is larger and less than respectively to the minimum and to the infimum and supremum doon sa buong closed interval. Okay? Tapos, ang gagawin ko ay what? I'll just multiply everything by the length of the interval. Okay? So multiplyin mo lang yan ng delta xi, delta xi, delta xi, delta xi. Okay? Totoo pa rin yung inequality kasi nag-multiply lang naman tayo ng isang positive constant sa lahat ng sides ng inequality. So fix yan. Tapos, kukunin ko yung summation. Okay? Dahil bawat isang term na ganito sa summation satisfies this inequality, so therefore ma-inherit ng mga summations yung property ng bawat terms. Dahil yung term sa I equals 1 ay totoo ito. So kung ito ay yung m times delta x1 ay mas maliit sa m1 times delta x1 and so on. Totoo siya sa bawat I. So pag kinuha mo yung summation, ma-preserve yung mga inequality. Alright? Tapos ang mangyayari dito, si M independent of N, of I, so pwede siya lumabas. Ganun din ito, lalabas siya doon. Tapos matitira na lang ay delta x sabay. Pero as we have mentioned, delta x sabay is just the length B minus A. So essentially, this guy is M, lumabas ng summation. Tapos yung summation ng delta x sabay ay equal lamang kay B minus A. Ganun din yung nangyari dito. Lumabas si capital M, natira yung summation ng delta xi, pero yun lang yung total lengths ng mga subintervals, meron tayong B minus A. Okay? So, totoo yan. Tapos itong mga nasa gitna, this is the lower Riemann sum, and this is the upper Riemann sum. And so that ends the proof. Na-establish natin yung unang inequality. All right? Hold on, guys. Give me a minute. Okay. So this is one major inequality, though hindi siya ganoon kahirap. You might think na obvious nga yan, sir. So kailangan natin yan dun sa mga ibang pagpo-prove ng mga susunod na theorems. But before we move further, let's define muna ano yung refinement ng isang partition. Now, if we consider two partition inducers, say P and P star of the same closed interval AB, we can say that P star is a refinement of the partition inducer P if P is a subset of P star. Okay? So kapag mas maraming elements, actually hindi lang basta dapat mas maraming elements. Kapag nadagdagan ng elements si P to get P star, then you can say P star is a refinement of the partition inducer P. Okay? So parang mas pinapino natin yung partition inducer, right? Kasi nagdagdag tayo ng mga panibagong partition points. Kaya siya naging subset, ano? So halimbawa, nag-start ka na ng P. Oops, baligtad. Halimbawa, ito si B equals X little n. Alright? So, halimbawa, ito yung partition P mo. Pag ang ginawa mo, nagdagdag ka pa ng mga partition, ng iba't iba pang mga elements sa partition inducer. So, ito set P, tas nagdagdag ka rito ng, say, y1, nagdagdag ka rito ng y2, y3, y4, and so on, hanggang makadagdag ka ng y10, alright? So pag nagdagdag ka ng kahit isa pang element dun sa partition inducer in the right position, ha? So dapat kasi ordered, kasi dapat partition inducer pa rin si P star. So dapat in increasing order pa rin yung elements ni P star starting from A hanggang kay B. So etong bagong partition inducer natin, consisting of the X's and the Y's, sila yung tinatawag natin na isang refinement. Kasi mas pino na o mas maninipis na yung mga subintervals dun sa partitions induced by P star. Okay? Tapos titingnan natin ano yung epekto ng pagre-refine ng isang partition inducer dun sa value ng lower at saka upper Riemann sum. Okay? So, okay. So, meron lang ditong isang example ng partition ng refinement. Kung meron ka raw P, siya ay si 0, 1, 2. We know that this is a partition inducer of the closed interval 0 to 2. Now, if I will add 1 half and 3 halves dito kay P in the right position, so look at P star there, habang sinasaksak ko yung aking pen. Si 1 half siningat sa pagitan ni 0 at ni 1. Si 3 halves siningat sa pagitan ni 1 at saka si 2. Na-preserve lahat ng elements ni P. Nagdagdag ako ng 2 additional members para mabuo si P star. In-arrange ko ulit sila increasingly. So, ibig sabihin si P star ay refinement ni P. The next question is, what happens to the lower and the upper and the lower sums kapag ka ni-refine natin yung partition inducer? Okay? So, lemma 5.2 answers that for us. If P star is a refinement of P, nagkakaroon daw tayo ng mas malaking partition inducer. Okay? So pag ni-refine mo si partition inducer P, mas marami na ka na ngayong partitioners, sort of, partitioners, para mabuo si P star, makakakuha tayo ng mas malaking value ng lower Riemann sum. On the other hand, pag nagkaroon tayo ng refinement, mas lumiliit naman yung upper Riemann sum. Okay? So, parang fake news itong nandito, ano? Na ni-refine mo na nga si partition inducer, bakit mas lumiit yung upper Riemann sum? So that's what we want to convince ourselves. Tingnan natin yung proof. Paano nga ba na-justify na totoo itong dalawang inequalities na to? Alright? So ganito yung ginawa. So nag-start ako kay partition P. Okay? Tapos, nagawa ako ng partition inducer. Okay? Nagkaroon ako ng refinement kay P and I called it P star. Paano ko din-define si P star? Kinonsider ko yung mga P sub I stars. Ang nangyari lang dito ay, nagsingit lang ako dito ng panibagong partition inducer. Okay? So originally, in the original partition inducer, okay, P, meron na tayong mga gantong closed interval, ano? Interval x sub I minus 1 hanggang kay x sub I. Now, para mabuo ko si P sub I star, magko-consider pa ako ng isang partition inducer dito naman. Okay? So, so dito, x sub I minus 1, x sub I. Siya naman yung gagawan ko ng partition inducer. Pwedeng meron ako ditong x, at tawagin natin y. Ang hirap mag-number eh. So, basta magdadagdag lang ako dito ng mga points na partition inducer. Tapos yung set na x sub I minus 1, tapos itong point na to, itong point na to, itong point na to, itong point na to, hanggang makarating ako kay x sub I. Ito yung tatawagin yung PI star. Kasi si PI star, siya yung partition inducer noong sub-interval x sub I minus 1. And if I proceed in this manner, pag kinuha ko yung union ng mga P sub I star, si P star ay isang refinement ni partition inducer P. Kasi na-preserve ko lahat ng member ni P sa union ng mga P sub I star and I added some bonus partition points. Alright? Pero dahil si P star ay isa pa rin, bawat isang P sub I star ay isang partition inducer, hindi nga lamang nung parent interval, pero nung bawat isang sub-intervals, gagana pa rin yung lemma 5.1. Totoo pa rin tong inequality na to. Pero si little m at saka si capital M, sila dapat yung infimum at supremum ng mga function values doon sa interval x sub I minus 1 hanggang kay x sub I. And we will denote that supremum and infimum on the ith subintervals to be little mi and little m and capital M sub I. Tapos itong gitna, ito yung lower Riemann sum with respect to the refined to the partition P sub I star. Ito naman yung upper Riemann sum para kay P sub I star. So basically, in-apply lang si lemma 5.1 on the interval x sub I minus 1 hanggang kay x sub I. Okay? And totoo ito sa lahat ng i's. Alright? So ang gagawin ko, kukunin ko yung summation ng bawat side na to as I goes from 1 until n. Okay? And you will notice na yung lower Riemann sum ni F with respect to the refined partition inducer P star ay equal lamang sa lower Riemann sum nung bawat isang partition inducer P sub I star. Okay? So ibig sabihin, pag kinuha ko yung summation yan, summation ito, summation yan, summation ito, ito, siya lamang yung lower Riemann sum ni F relative to P star. Ito naman yung upper Riemann sum ni F with respect to P star. Okay? Tapos, saan equal to? Yung summation ng M sub I delta X sub I. Ito ay equal lamang sa lower Riemann sum ni F relative kay P. Kasi yung mga M sub I, sila yung mga infima doon sa mga subintervals induced by the partition P. Ganon din ito. Pag kinuha ko yung summation ng mga big M sub I, delta X sub I, ito yung magiging upper Riemann sum ni F with respect to the partition inducer P. Kasi dito, bawat isang M sub I ay maximum o supremum ng mga function values dun sa ith subintervals. So by definition, this will just be the lower Riemann sum of F or the upper Riemann sum of F with respect to the partition inducer P. Okay? And putting all those together into one giant inequality, we'll get this line. Okay? And here we see that the lower Riemann sum prior to the refinement is smaller than the lower Riemann sum after the refinement or at the refinement. And also, the refined upper Riemann sum is smaller than the original upper Riemann sum. All right? Clear ba yun? Medyo algebraic lang yung mga proofs, no? Pero I hope nasusundan siya. So, yun yung epekto. Pag nagre-refine ka, mas malaki yung lower Riemann sum, tas mas maliit yung upper Riemann sum, which makes sense. Kasi di ba alam natin, gusto natin kunin yung parang ang ideal para ma-define yung integral, dapat papadamihin natin yung partition points. Okay? Yung subintervals na ginagamit. So, yun yung dahilan kung bakit pag nirefine yung partition inducer, lumalaki yung mga yung mga lower Riemann sums. So nadadrive natin sila pa kanan. Tapos yung mga upper Riemann sums, habang nire-refine natin yung intervals or yung partition inducer, lumiliit yung values nila. Kasi by this inequality, mas maliit yung refined upper Riemann sum. And kapag lumalaki yung lower Riemann sum, lumiliit yung upper Riemann sum, there is a bigger possibility that they will meet in the middle, which is what we want, right? Kasi gusto natin maging equal yung supremum ng L at infimum ng U para magkaroon ng common value na tatawagin nating integral ni F on the closed interval AB. All right? Hindi pa dito natatapos yung serye ng mga lemmas o mga preliminary results na kailangan natin para mapag-usapan ang integrability criteria. So we can move on to lemma number 3. Ito naman yung relationship ng lower at saka upper Riemann sum pagka magkaiba na yung partition inducers. Kasi alam natin, kapag meron kang fixed na function f at partition inducer p, laging alam natin yung lower Riemann sum ay laging mas maliit sa upper Riemann sum. Pero dapat parehas yung partition inducer. Ito yung isa sa mga results natin kanina, no? Mas generic yung sinasabi ng lemma 5.3. Sabi ng lemma 5.3, ang lower Riemann sum ng kahit anong partition inducer ay dapat mas maliit or equal to sa upper Riemann sum kahit sa ano pang partition inducer. So ibig sabihin, wala tayong mahanap na isang pares ng partition inducers na yung lower Riemann sum ay magiging mas malaki kesa dun sa upper Riemann sum. Kung lower Riemann sum ka, kahit ano pang partition inducer ang gamitin ko sa'yo, hindi ka magiging mas malaki sa kahit ano pang upper Riemann sum. Yun yung idea ng lemma 5.3. As long as you are a lower sum, regardless of what partition inducer was used to get you, hindi ka pwedeng maging mas malaki sa kahit na ano pang upper Riemann sum, even if how refined the partition used to find the upper Riemann sum. Ito yung medyo actually mind-boggling nung binabasa ko to nung last semester. Totoo ba to? Parang napaka-generic nung claim, ano? Parang pag lower ka na talaga. There's no way to go up. Hindi mo matatalo kahit isa sa mga upper Riemann sums. And apparently, the proof will require yung refinement, yung nasa lemma 5.2. Kaya dapat serye din i-discuss itong mga lematas na ito, no? So, ano yung sabi? Paano siya pinrove? There's an ingenious proof to this. Ginamit niya yung fact na si P1 union P2 ay refinement ni P1 at saka ni P2. Alright? Bakit? Kasi si P1 ay subset ni P1 union P2. So, ibig sabihin, lahat ng members ni P1 ay nandito nasa P1 union P2 na plus some bonus points na nanggaling kay P2. So, indeed, this is a refinement of P1. And also, it is a refinement of P2 because all members of P2 are in P1 union P2 plus some added bonus partition points. All right? So, ibig sabihin si P1 union P2 ay parehas refinements ni P1 at saka ni P2. So, what now? Well, remember kapag ni-refine natin ang isang partition, nakakakuha tayo ng isang mas malaking lower Riemann sum. And that's what we get here mula sa lemma 5.2, right? Yung lower sum ng isang partition ay mas maliit or equal sa lower sum ng isang refined partition. On the other hand, I'm going to use the fact that P1 union P2 is a refinement of P2. So, ibig sabihin yung upper Riemann sum ni F relative kay P2 ay greater than or equal sa upper Riemann sum ng kahit ano niyang partition, in particular kay P1 union P2. Okay? And then we know that the lower Riemann sum of one partition, in particular ni P1 union P2, ay hindi pwedeng mas malaki sa upper Riemann sum ni P1 union P2. So that establishes this inequality, right? Kasi pag same partition, lower sum is always less than or equal to the upper sum. Kaya lang, ito ay mas malaki kesa dito. Tapos ito, mas maliit kesa dito. So therefore, by transitivity, the lower Riemann sum of F relative to P1 ay dapat mas maliit sa upper Riemann sum ni F with respect to P2. And hence our result. Pag lower sum, lagi yung mas maliit or equal sa lahat ng mga upper sums. Okay? And with that, I think we're ready for dun sa kulang. Remember, before we started this lematas, meron tayong sabi natin yung mahirap i-prove. Ito, yung nasa gitnang inequality. Yan na yung nasa lemma 5.4. Okay? Na yung lower Riemann integral ay laging mas maliit or equal sa upper Riemann integral. And this is a big help because from now on, if we want to use the definition to prove Riemann integrability, with lemma 5.4 proven, ang kailangan na lang nating ipakita ay ito. Oops. Pag na-prove natin yung lemma 5.4, tapos sa isang particular example, na-prove natin na yung lower Riemann sum ay greater than or equal to sa upper Riemann sum, ibig sabihin, mako-conclude na natin ng lower Riemann sum ay equal sa upper Riemann sum. when we conjunct these two things. So using the definition of Riemann integrability now boils down to proving this reverse inequality. Kasi yung isang inequality ay automatic na. Yun yung ipoprove natin sa lemma 5.4. Na yung lower Riemann integral ay laging mas malaki, ay laging mas maliit ay or equal sa upper Riemann integral. Okay? Now, medyo clever then yung proof. You see here, ilang lines lang yan? 4 lines or 5 lines. Tapos ang ganda ng proof na to. So tingnan natin paano siya ginawa. So nag-consider ako ng isang partition inducer ng closed interval AB. Tapos, alam ko na ang lower Riemann sum ay laging mas maliit or equal sa kahit ano pang upper Riemann sum. So I know this, that the lower sum of f with respect to p is no greater than the upper Riemann sum of f relative to all partitions p prime ni closed interval AB. This is by lemma 5.3. Okay? Tapos, makikita natin dito ay si L, etong lower Riemann integral of f with respect to p, ay isang lower bound ng lahat ng upper sums. Kasi ito, arbitrary si p star, si p hat. Si p prime. So, ibig sabihin, si p prime kasi kahit anong partition inducer ni AB. So, ibig sabihin, ito ay lower bound ng lahat ng mga upper sums. Okay? So, dahil yung upper Riemann integral ay infimum o greatest lower bound ng lahat ng mga upper sums, and yet L is a lower bound. So ibig sabihin, etong lower Riemann sum na to ay bounded above by the upper Riemann sum. Again, this is true because this is the greatest lower bound ng mga U. Tapos sabi natin si L ay lower bound ng mga U. So ibig sabihin ng LFP ay lower bound para din sa upper Riemann integral. Okay? Tapos ngayon, babalik rin ko yung argument. Si P naman ay arbitrary, right? Wala tayong binigay na condition para kay P. Okay? So ang masasabi ko ngayon ay, okay, si P pala ay arbitrary, tapos totoo to sa kahit anong P. So ibig sabihin, itong constant value na to, itong fixed value na to, ay isang upper bound para sa mga lower Riemann sum. Sa kahit anong lower Riemann sum, upper bound niya yung upper integral. Okay? Kaya lang by definition, yung lower integral, siya na dapat yung least upper bound ng mga lower sums. Okay? Ito ay upper bound ng mga lower sums. Ito na nga yung ito na nga yung least upper bound. Siya na yung pinakamaliit na upper bound. So this least upper bound must be greater than the upper bound that we have established, which happens to be the upper Riemann integral. So that ends the proof. Now, laging mas maliit yung lower Riemann integral kesa sa upper Riemann integral. Okay? So, and then, if we'll be able to show yung reverse inequality, then magpa-follow na kagad yung equality ng upper at saka lower Riemann integral. Okay? Medyo, actually, natuwa ako sa proof ng 5.4. Napaka-clever nung pagkakagamit ng arguments. Dumaan muna siya dun sa pag-establish na upper sum para mapalabas yung ng lower bound, para mapalabas yung upper integral. Tapos binaligtad niya yung argument, finlip niya yung argument na sinabi niya naman, yung upper integral naman siya yung upper bound para sa mga lower sums. So ibig sabihin, dapat mas malaki siya doon sa least upper bound. Okay? And that ends proof of lemma 5.4, and I think this is a good place to stop. Saktong-sakto, one section down. So at this rate, I think we're gonna finish the unit in 3 more meetings. So kaya sabi ko siguro pwede na ako maglabas ng problem set over the weekend. Okay? Tapos ang deadline naman niya ay June 9. So para meron kayong 2 or 3 weeks para tapusin siya. Okay? Actually, hindi na pala, no? Ilang weeks na lang. Parang mali yung bilang ko. Yung nasa isip ko. So we have 1, 2, 3. Mahaba pa naman pala. We still have almost 3 weeks after this week. So we're still good before the end of classes. Okay? So any questions, guys? Galawin nyo naman yung baso kung may tanong kayo. Ang hirap, ang tahimik nyo. Okay, so I hope everything is good. Oh, by the way, my apologies pala for late grading your homework number 5. Actually, pati yung homework number 4. Kasi dun sa mga kumusta questions ko, medyo ano na pala, medyo wala na sa timing yung mga naging sagot ko. So, but I hope you still read those. Yeah, kasi binabasa ko talaga kahit yung mga comments nyo. I really would like to have an insight about your about how you are doing and coping with this setup. And thank you guys for sharing some things. And yeah, kung kailangan nyo ng sounding board, tama ba? Sounding board man tawag nun, or somewhere to vent, just make use of those quizzes, or homeworks, or you can even write me an email if you badly need somebody to talk to or to vent off your feelings, lalo na ngayong mga trying times. Okay? So yeah, I think that's it for now. Wala naman kayong tanong, so thank you for letting me know. So let's call it a day and just meet again on Thursday, and we'll continue with section 5.2. So until then, keep safe, guys, and kita-kits tayo sa Thursday. Bye. Oh, did I press the recording on? Okay, good.